Okay, so now let's answer the question that if this is a clarification. So number one. So does guessing makes the memorization larger? So for example, if my prediction function is a function, so if my prediction process is a function, that means for any input, so this is my input string, the output is deterministic. So there's a function, and in this process, we can, for example, we can use the greedy algorithm to say that I'm using for the same input, I'm using the output with the highest probability to as the prediction. But for generative model, you can actually sample this output. And my question is. For example, my question is for memorizing the first block. For example, the first word after the generation. So this is my input. San Francisco is a. Here we have a beautiful city, and this will be my first word. So does sampling am I able to achieve a rate of higher memorization for the first block if I do sampling instead of greedy generation? The answer is you could if you do multiple sample, there might be cases that you can have this the rate of generation larger, but if you sample multiple times, the expectation or the ratio is not going to be higher. And here's a proof. I don't want to call this a theorem because it's almost trivial. So let's consider the probability the first the first block output. Let's just, for simplification, let's say output is memorized. So output is memorized. This means so memorization just means the generated output equals to the actual result of this data. So this probability would just be the probability that the generated output, so generated block, let's say, output is equal to the actual data at this point. Here, it will be clear. So you know the generated first block is equal to the actual output, and this thing you could say, okay, I have two processes. The first sampling is that I sample the data from the training data. So the whether actual data is equal to x is depend on my sampling from the data. And here, the generated the distribution of the generated block is given the input. I'm sampling the given the generated output with my model given my input. So this will be another sampling. So let's say so this is actually we can take the summation of the possible outcome. So let's say a summation of all the possible y's. So this will be probability generated output is equal to y. small y. So and given given the input, given the input and given the given the actual actual output of the data times times the probability that actual equals to y. Actual data also equals to y given the input, right? This we can decompose this, but then when you think of the generation of y given the input, the generative process, because when the model generates the new token, all it knows is the input. It doesn't really know. Well, so the generated process given the input, it's not depending on the actual output. Let me illustrate why that is the case. When, for example, if my input is San Francisco is a beautiful city, it is this is a input. San Francisco is and something else, and I want to generate this thing. So maybe there's in the training data, maybe there's maybe one sentence so data. So training data one is San Francisco is a beautiful city. And the second training data is San Francisco is a good city. So these are my training data. So when I'm generating this, all the model is given is this. When the model sample here, it is going to sample from possible output that it thinks is possible, but maybe the possible output is outside these two. Maybe there are some other values the model thinks is possible, but the model is not going to know whether in the sample data you chose this one or chose this one. So it could be let's further simplify this by example. So if the training if the output is San Francisco is a beautiful city and San Francisco is a good city, this and then it means that there could be cases when the generated output is San Francisco is a good city, but in this case the actual is San Francisco is a beautiful city. There could also be cases that when the generated case is San Francisco is a beautiful city, when the actual data that we picked is San Francisco is a good city. So the generated process doesn't know which sample we picked during the data sampling process. So we can think of these two. Let's say so we can write generated. So the generated output is independent to the actual to the actual output given the input when when the weights are the same and assume no duplicates. So if this is given, we can safely cross out this one, and then you become generated and actual with given the input. So this will be the idea. And once this happens, we can further simplify this to say, let's say the actual. So the actual. So let y be all the possible tokens, and the actual equals to y given input. We can denote it by let's say actual equals to yi. This is yi in the space of y, and we can denote this part as pi, and this one as a qi. So what we have is the sum let's say, well, we don't need a y anymore. We just need I, right? So this will be pi times qi. But there's a restriction. The restriction is that sum of pi. So well, actually we don't need to restrict the p, but it's for now it's good to write this term and the you know the maximum probability here is when this thing is maximized, and is you could see later it's really simple to optimize this given our restrictions. Uh, okay, and okay, and then let's say I want to optimize maximize uh, pi PIQI with restriction that P and Q are conditional probability. So if you sum over I, then this will be so sum of Qi is 1, sum of Pi is also 1. And since this is probability, we also know that Qi is greater or equal to 0, Pi is greater or equal to 0 for all I. So here's, yeah, you could see that more clearly, maybe. Yeah, and maximizing this is quite simple because uh, because we have this restriction. We cannot really actually maximize pi because the way we sample the data is just the weight itself is the distribution of the data itself. So pi is fixed. All we have to do is qi, and I want to show that the argmax q is such that q is equal to 1 for um, for for i's with for I equals to max I pi and 0 otherwise. And this is just greedy. Well, not the greedy inference, but this is for the uh, inference when for the maximum posteriori for the one term for the one block maybe for one block, because this is just saying that if the inputs are all the same, I will pick the output that has the largest probability for this stuff. So this means if I have San Francisco is a beautiful city, and it also has good city, but I don't care about the rest of the world. I just care about this block. This thing just says if San Francisco is a beautiful city and something else is repeated in well has maybe 12 occurrence in the training data, and good city has like 18 occurrence data, it will always go this path. You always pick this path because this is the maximum. This is the one with the maximum weight in the training data. So this is what I mean. Um, and and any other sampling any other sampling cannot achieve this maximum. And why? This is because we can compare Q. Well, this is a quite simple optimization problem. So if you know optimization pretty well, you could probably just directly see that. But in the case that you don't see it, I'm still going to formulate this. So if I have compare Q, which is a um, so let's call this one Q star. Let's call this Q star, and let's compare another Q that's not equal to Q star. Uh, so Q not equal to Q star, but the sum of Qi is still one. That means for I equals to maximum pi, so that I will call this argmax pi, right? So this I equals to uh, so um, so for maximum so for argmax pi, q argmax pi is not equal to 1. Actually, it's less than 1 because it cannot be, the conditional probability cannot exceed 1. And if that happens, uh, there should be some other values of Q that's greater than 0. Otherwise, it doesn't sum to 1 anymore. So there will be, so if it's smaller than 1, we can denote maybe d equals to 1 minus q argmax p. So this will be d, and there will be, let's say, and all other values. So sum of q which index are not in the argmax p. This one equals to d, right? And I can pick one entries from here. So let's say these are all the indices that are not corresponding to the maximum p. I can call this maybe the first value. I can pick any value, but I can choose one value. Argmax p1 is greater than 0, and I can construct another q prime. So how do I construct it? Q prime argmax p. I can add this value to the argmax p, so that this q prime argmax p equals to q argmax p plus this thing, q max p bar 1. So and then q prime, let's just use the index we choose that does not correspond to a maximum of p. Argmax p bar. So this value we change it to 0. So what happens is that you can prove that so what happens is that we're gonna prove that pi q prime I, the sum is strictly greater than pi pi qi. Why? Because the only difference between this sum and this sum is in these two terms. So simple algebra here. So let's say so here the difference between these two, we just need to prove that pi qi prime minus pi qi is equal to which term? So actually we just need to compare the argmax of p and the argmax bar argmax p1 bar, which we chose that with the original probability greater than 0, but arbitrary. Choose one arbitrary. With the index, we chose an arbitrary here. So because the only difference in the terms, this one minus this one is here. So let's write it out. This will be p p argmax p. So p argmax p q q argmax p prime minus q argmax p and plus p. This one is the one that we chosen are not the max of p. Argmax p1 q argmax p1 bar minus q. Q prime argmax p1 bar minus q argmax p1 bar. And we defined it in such a way that that this one is just 0 because we put it into here, and this one minus this one is just the original of this one. So this becomes now p argmax p q argmax p1 bar minus p argmax p1 p argmax p1 bar q argmax p1 bar. And this should be very clear that you can factor this thing out, and it's just equal to this is just equal to q argmax p1 bar. So this is remember this is the one this is a term of q that we chosen with correspond to the p that's not does not take the maximum probability, and that q has greater than 0. So this is greater than 0, and the remaining we have this subtracts this. So it is but if you look at this term, what is this? This is the term that corresponds to the maximum p. So this is just the max p, right? This is the max p. Or p max, or whatever you want to call it. So this is the maximum term of p, and this one is a term of p that takes a value that's less than the maximum p. So this is something smaller than maximum p. So what happens is that we have this number is greater than 0, and this part is also greater than 0. So that means this is greater than this one. That just means our new qi prime is greater than a qi. And if you continue doing that for at most case steps, you end up with we can take. So if q prime is not equal to q star, remember that q star is 1. It takes 1 for the argmax argmax p and 0 otherwise. Well, suppose that argmax p has no duplicates, but if it has duplicates, it's also fine because you just pick one of them. So if this is not equal to this, you can continue construct the q prime which has this property. So q prime is greater than pq prime, equal greater than pq, and you know, and after at most at most this steps after at most the cardinality of y steps, uh, you reach you reach q star and you cannot move anymore. Uh, so and this holds for any comparison of q star with the other arbitrary q. So that means q star is the optimal. So this completes the proof. But I also want to show you that this well, not in the sense of algebra, but in the sense of geometric. What does it mean? So let's say we have a slope of something that has so I want to optimize PIQI here with pi is greater than 0 and q is 1. Um, that just means if you take if you take the derivative, you just get what? So so partial derivative between this and the q is just uh, uh, well, it's just pi, is it? Yeah. Well, if you expand it, it's just the p1, p2, and p p all the possible outcomes. And here somewhere you have p max. And the thing is, you want to claim for 1 unit, and how do you distribute the weight? So you want to distribute the weight in its linear term to the maximum term. So this is geometrically you can think about that. I can't draw that picture. I don't think. Yeah, maybe you have. So this is Q1, this is Q2, um, and you have so your surface has a slope here and has a slope here, and you want to climb along the uh, let's say Q1. Let's say Q1 and Q2 are both positive, so you are restricted to this area, and you want to climb on the top. So it's you should climb on the. If everything is linear, you should choose the slope with the maximum gradient. So this is I think this completes proof. So yeah. So yeah. Hope it works. Hope it works for you, and hopefully make it a little bit clearer.